All right, this week, lecture 8 and 9, all about animation the entire week, and your assignment number 4 is all about animation. In fact, your assignment number 4 is just animate your assignment number 3. So we're going to really go deep dive and not really talk about much of anything else this week and try to understand how animation works. It's a very important topic in iOS. There are lots of different parts of animation, and you can see I have a lot of demos queued up. I have this slide up here mostly just so you can refer to it later because it's a list of the things that we will have done once we've done them all. But I am going to make a little detour at the very beginning. You see that top miscellaneous topic. This miscellaneous topic really has nothing to do with animation whatsoever, but I just never found a place to slip it in. So we're just going to take a couple of slides time out and go talk about this. So what is this that I'm talking about? Well, it's property observers and a similar related thing called onChangeOf, which we use in Vue. We know that Swift, all these value types, it can detect when things are changing. Functions are marked mutating, so we know which ones are going to modify things. And vars, it knows which vars are gettable and settable, etc. So you can kind of stick your nose in there, and when a var, when its value gets set, you can observe it. That's what property observing is, basically observing the changing of a var. Now, I'm putting this code up here, and the most important thing to get out of this slide is that middle sentence, which is that this syntax for property observing looks a lot like computed vars, but it is completely a different thing. It has absolutely nothing to do with computed vars. So even though it looks almost the same. So what is this syntax here? So I've got this var is face up. It's a normal var, like in our card. It's a normal stored var, not a computed var. But I want to observe when it changes. Now, this particular example that I made here is for the pie. You know, we have the countdown pie that we built the shape of, and then we're going to animate it this week. Well, every time face up goes to true, I want to start using that pie's time. And every time it goes back face down, I want to stop using the pie. In other words, I don't want the pie to be ticking down when the card's face down. Here I'm saying, I got put a little curly brace after it, like a computed var in syntax, but totally different in terms of semantically what's going on. And then I say will set, and then another curly brace. And then in here, this is code that's going to be executed when is face up is about to be set. And in there, there's a special var called new value, which is the value that is going to be set to. Simple enough, right? So here in will set, if the new value is going to be true, in other words, it's going to be face up, I'm going to start using the bonus time. If the new value is being set to false, I'm going to stop. And this is going to happen every single time is face up gets set. However, not on its initial value. So if I were to say var is face up colon bool equals false, which is what we do in our thing, and then have this curly brace after, it would start out false, but this will set would not be called. That wouldn't matter here because, of course, we start out with stopped bonus time usage, but it doesn't get set on that initial value. But every other change to it, this gets involved. And there's another one in addition to will set called did set, and that gets called right after is face up gets changed. And in that one, the magic variable in there is old value. That's the old value. Okay, just got set to a new value. So that's property observing. It's really kind of cool and powerful and great for doing things exactly like this. We're going to use it a couple of times this week in animation. It's especially valuable to use in your model, I find. Less valuable in your Vue. Why is that? Well, let's talk a little bit about what's going on inside of your Vue and Vue model. You've got this situation where changes are happening. You're observing them. Either they're changes in @sign state or they're changes in @sign published vars in your Vue model, and it causes your Vue to redraw, right? We have this reactive Vue system, and every time it sees changes in those things, it's redrawing. Well, if you're observing some property, you want to be doing the things you're doing in sync with that redrawing. So we don't use property observers in @sign states. Instead, we use something in our Vue called onChangeOf. It's a Vue modifier. You can put it on any Vue, and all it's going to do is execute this closure that comes with it whenever this changes. So this can be almost any expression in here, and if that changes, it's going to execute this closure. So the example I have here is I want to keep track of how many times I've tapped on cards. So I'm just going to watch my view model's cards, and every time it changes, I'm going to increase my number of taps by 1. And I'm actually showing my taps in a text view, and I've attached this view modifier to this text view. I could really attach it to almost any view, but I've just attached it to the view where it's having the most effect, keeping track of its taps. And notice that it takes an argument disclosure, and this is the new value that this is going to have. So view model.cards is going to change. This is what it's going to change to. Now, I don't happen to use that in taps plus equals 1, but you could use the new value that it's changing to. So this is the thing we use when we want to track changes in @sign states and @sign published vars. Okay, back to this animation thing. So I told you at the beginning of the quarter, I'm going to try and teach you everything in this class at least 3 separate times. Once I'm going to tell you about it in slides, then I'm going to show it to you with a demo, and then you're going to do it in your homework. And that's very much true for animation. So here's the part where I'm going to tell you about animation, all the parts of it, how it works, etc. Let's start with the kind of basic fundamentals of animation, things you need to know to really understand what animation is about. And the number one thing to understand is that animation is just showing you change in your model, usually, over time. That's all it is. It shows you change over time. And this change gets reflected through view modifier arguments, and obviously shapes can be changing. And also, I call this out as a separate thing, but you're going to see it's actually just a variant of the first thing there, which is views coming and going from screen, right? A view comes on screen, you want to fade on, okay? Or it goes off screen, you want to fly off or something like that. That's views coming and going. So those are the 3 things, the 3 kinds of changes that are happening that we're trying to animate. This is probably the most important line on this slide. Animation is showing you changes that have already happened, and it's just showing them to you over time. This takes some getting used to for people who haven't done asynchronous programming or something like that. You just want to think that if I have some animation that's taking 5 seconds, that's animating the opacity or something, that the var that sets the opacity is somehow changing over time. But it's not. When you set the opacity to 1 from 0 and it fades in, when you set it to 1, it instantly changed to 1 in your entire view. It's just that the animation system showed it to the user over 5 seconds, right? So everything you see that's animating instantly happened, and it's just showing you over time. Once you get that in your head, it'll make a lot more sense how animation fits into all the other things that you're doing. So view modifiers are the primary change agents in the UI. Most of the stuff that's changing, like opacity, aspect ratios, even views flying around, is just the position view modifier. There's a view modifier I haven't showed you yet called position, which, like HStack and Lazy VGrid, they use that modifier to position their views in there. When things flying around, it's just because that positions arguments are changing, right? So view modifiers are really what makes everything go, and you're really going to see that in the demo that we do. One thing you have to understand about changes to view modifiers arguments, though, is they're only going to animate after the view has been put on screen. So this view is going to come on screen with a certain opacity and a certain aspect ratio. That's not going to, when it comes on screen, animate from some random value. It's going to be that value when it comes on. And then if it changes, then you're going to see the animation. People sometimes get confused. They'll set their opacity to something and they're expecting that their view will, somehow animate to that opacity, but it wasn't on screen, so it had no previous value. So it starts with the value it has when it comes on screen. And not all view modifier arguments can be animatable, but I would say the vast majority is 100% of the ones that you would think you could animate are animatable. When a view arrives or departs on screen, when that animation happens, the entire view is animated as a thing. So the whole thing fades in, right? Or the whole thing flies off, or the whole thing scales in or out in size. And a view coming on screen is only animated if the container that it's in is already on screen. So if a view comes on screen with its container, then it's not going to get animated. You only get animated if you come on screen and you're already in a container view that's already there on screen. And same thing, if your view is going off screen, it's only going to get animated if it's leaving some container that's staying on screen. Because if the container goes off with you, then the only animation going to happen is whatever the container is animating. Now, how do views come and go? How do they come on screen or leave? Mostly if else is in view builders, right? You have if this is true, then show this view, else show this other view. Well, as that if changes, one view is coming and the other view is going, right? It's appearing, disappearing. Also, for each is a sneaky way for views to come and go, because for each is like taking an array of things and building a view for each of them. Well, if you take something out of the array, it's going to take the view out that goes with it. So that's a way for a view to go away or to come back in if you add it back to the array. This is the primary way that views come and go: if, else, or switch statements inside of a view builder, and for each. So how do we make animation happen? How do we make it go? And there's three ways to do that. One is implicitly, and this is the animation we saw for shuffle. And the idea here is we're going to use this view modifier called animation, and we're going to make it so that everything that affects, the view that we apply it to, is going to get animated when things change, and we get to say what value, what thing has to change to cause this animation to take effect. So we could actually put multiple implicit animations on something with different values, so different things would cause different kinds of animation to happen. So that's implicit animation. That's all you've ever seen in this course. Secondly is explicit animation. Now this one, we wrap something that we're doing with this with animation thing right here, and it causes all things that changed because of what we did inside there to animate together. This one is actually the primary way we do animation, not the implicit. We do it with this explicit. And one of the first things I'm going to do in the demo is switch over from the implicit animation we were doing to explicit animation, which is how we would really do it. And then the last way that we cause animation to happen is by including and excluding views from the UI, because I told you that we can set what kind of animation happens if we remove a view from the UI. Does it fade out or whatever? So that's something we can do, you removing them or adding them, that will cause animation to happen. And these are really the only three things that cause animation, right? Now, all of these things, though, again, only happen if they're happening in views that are already on screen. We can only animate change after we come on screen. I've said this twice already. This is the third time, I think. I just want to get this in your head, because in your homework assignment, you're going to try and do something, I almost guarantee it, and you're going to be like, it doesn't animate. Well, it's because it came on screen that way. You didn't change it after it came on screen. All right, so let's talk about implicit animation here. This is what some people would call automatic animation. And it's essentially, it's a view modifier, right? So it kind of marks a view so that all the things that are happening to that view before that view modifier is added, so all the opacities and aspect ratios and other kinds of view modifiers you put on that view, changes to those will get animated as long as the value is true in the dot animation, according to some animation curve. We'll talk about what this animation curve is. If you remember that dot animation that we did, it had an argument, right? The first argument there, you see it says simply add dot animation. There's that animation argument. What is that? That's specifying this curve and duration of the animations. Here's an example. I've got a ghost right there, and he's got some card. Maybe this is the ghost. This is a piece that's the ghost of some card game that's better than the one we have, and it's got scary cards, and it's got upside down cards and other kinds of things. And you know, when the card's scary, it shows it to you, and when it's not scary, it hides it with its opacity. And it's also got something here called a rotation effect. That's just another view modifier, and so it knows how to be upside down. Rotates itself 180 degrees to go upside down. And when I put this dot animation, and I've used an ease in out animation here, it causes both of these to get animated. If I were to put this animation right up here under the ghost, neither of these would get animated. If I put this in between the two, only the opacity would get animated, not the rotation effect. So where you put the thing determines which things are getting, only upstream things get animated there. And if I didn't have this dot animation, just took it off completely, then these things would happen instantly. There would be no, and that's assuming there's no explicit animation going on. We're talking about implicit here. If we took that, they would just instantly happen. And we saw that before we put our animation on our cards. We were clicking on things and they're instantly turning over. We had shuffle, they instantly shuffle. You know that without some sort of animation, things happen instantly on screen. This warning, dot animation, implicit animation, works more like font and less like padding. So if you put dot animation on a VStack, it's almost like you put dot animation on everything in the VStack, right? It kind of propagates in. And that can be confusing a little bit. And to be honest, we don't usually put dot animation on a VStack. That would be unusual. Usually dot animation, this implicit animation, it's less often used, and we're usually putting it on the Lego brick views, right? Texts or some view that we've created, that we've constructed out of other containers or whatever. So that's just something that can kind of confuse you. You put dot animation on a VStack and you're like, what? What's going on? You know, the things inside are being animated, but in a way it makes perfect sense that it does that, but just something people get surprised by. Now let's look at that first argument, that ease in, ease out thing, the animation curve. And that's called an animation struct. It controls how the animation proceeds, and it lets you control some things about the animation, like its duration. How long is it going to take for the system to show this change to the user? 1 second, 2 seconds, whatever. You can also control whether to delay the animation. This is especially true when you've got two little pieces of animation. You want one to happen first, and then you want the other one to happen. Maybe you delay the first one by half a second, and then it kicks in. You can also decide whether the animation repeats. Is this an animation just keeps going over and over, or how many times it goes, or whatever? It can even repeat forever. And you get to control its curve, the animation curve. Now, what do I mean by animation curve? The animation curve is how it splits up the time it takes to animate. So ease in, ease out, which is ease in, out actually it's called, which is kind of the default, I believe, animation. It starts animating it kind of slow, but then picks up speed and then kind of slows in at the end. And that's so that views don't jerk out of their locations, but they still get to where they're going quickly. Does that make sense? That's as opposed to linear, which is it goes from the start to the finish at exactly the same speed. And there's a bunch of other curves like a spring, which is an interesting animation. That's something where it gets to where it's going pretty quickly, but then when it gets there, it kind of vibrates a little, like it was on the end of a spring. And you know, some things when they fly across the screen, you don't want them to just land and stick. You want them to kind of land and give a little soft landing, as we call it there. And all of this stuff is in this animation struct. You want to go look at the documentation for animation. You'll see all the things that you can do and all these curves and all the settings you can do. There's really not as many as you might think because you don't really want to have too many different kinds of animation curves going on. The user will get a little bit like, whoa, what is all going on my screen? Automatic implicit ones, as I said, they're not really the primary source of animation. We use them mostly on leaves, leaf views, and also we use them for animations that are very much independent of all other views. Right? If animations go with a whole bunch of other views, then we're going to explicitly animate the change that causes that. And we'll see that in the demo, what we do there. Now, the most likely cause of animations in your app is going to be user interaction. The user is going to tap a card. The user is going to hit the shuffle button. That's going to cause a lot of animation to happen. Those are explicit animations. We're almost always going to use explicit animations to react to change. Don't make your UI react to change by putting a whole bunch of dot animations in there. Instead, you're going to, in the place where you make the change, usually calling a viewModelIntent function, you're going to wrap it with an explicit animation. So let's talk a little bit more about explicit animation, how it goes here. As I said before, it's essentially just wrapping a block of code, things that are going to be animated together. So here's an example of it. You see I've provided a linear animation here, 2 seconds long. And whatever happens inside here, this do something that will cause viewModifier shape arguments to change, that's all going to get animated together with that curve, a linear curve 2 seconds long. Explicit animations almost always wrapped around a view model intent function, it'd be extremely unlikely you would have a view model intent function called without wrapping an explicit animation around. You might, but it's pretty rare that you would do that. Red text always means pay attention. Implicit animations have more power than explicit ones. So if I explicitly animate something and inside there's a dot animation, that dot animation is going to win. And that makes sense because remember, we're putting dot animation on somewhat independent animations. So we don't want those independent animations to be affected by whatever's globally going on animating. And you'll see that very clearly in the demo. All right, let's talk about transitions. So transitions are this thing about views coming and going. We call those transitions. So get used to that word transitions. That's what the view modifier that does it, that sets it up is called. And they only work for views that are CTAAOS. That's my nice acronym there. I couldn't actually come up with any phrase that would be a word. So I picked this particularly hard to say, CTAAOS, so it'll stick in your mind, right? CTAAOS is containers that are already on screen. So if you want a transition to happen for your view, you have to be in a container that is already on screen. Underneath the covers of a transition, it's actually nothing more than a pair of view modifiers. A transition for coming on screen is just one view modifier that has the arguments of that view modifier before it comes on screen, and another view modifier that has the arguments for that view modifier when it is on screen, and it just animates between those two view modifiers as it's coming on screen. And you might have another pair for going off screen, view modifier, what it looks like just before it goes off screen, and then another view modifier with its arguments set for when it is off screen, and it just animates between those two. So that's all under the covers though. Above the covers, it looks like a transition is a thing, like opacity transition. Now, an opacity transition is just a view modifier with, opacity 1 and another view modifier with opacity 0, but that's all under the covers. You don't care about any of that. You're just going to say transition.opacity, and you're going to get that transition. You can also, of course, have asymmetric transitions where it fades on screen, but then it scales down to disappear when it goes off screen. In that case, you'd have 4 view modifiers, the 2 for fading in and the 2 for scaling down or flying away or whatever. We mostly, 99% of the time, use pre-canned transitions, and we find these not in a struct called transition, unfortunately. It's a struct called any transition. I'm going to talk a little bit about any transition here. Any transition is a type erased transition struct. Now, I'm not going to talk about why we do type erasing, but from your standpoint, just think of the struct that does transition as any transition, even though that's not really true. That's where you see them all. That's where you're going to go in the documentation to see what kind of transitions you can do. That's where all the static lets are that define all the well-known transitions, etc. So what are some of these things? There's opacity, that's the fading in and out. There's scale, so that scales in and out. So that's a view that would like shrink down to nothingness when it disappears, or if it's appearing, it would shrink up from nothingness to its full size. Offset's an interesting one. That's how it would fly off screen. So offset just takes it from where it is and offsets it by a certain amount. You get to specify how much. There's also things like move to the edge, where it'll fly off to the top edge or the right edge or the bottom edge, etc. And of course, you could define your own transition using this modifier version, which has the active and identity view modifiers, the pair, the 2 sides of the pair that it's going to use the before and after of the transition. So you can define your own, even just using this type erased thing there. So how do we specify a transition? How do we say when this view goes on screen or comes off screen, use opacity or use scale or whatever? You do it with this dot transition view modifier. Now here I have kind of a pared down card. Okay, it's got a face up and a face down. Fewer lines of code than ours, but you get the idea, right, everyone? Right? We got a rounded rectangle. We got a stroked rounded rectangle with the text on it, and then in the back, we've just got a filled rounded rectangle. There's actually 3 transitions on this slide. The text is going to transition by scaling up from 0, size, whoop, up to its normal size. And it's going to disappear by starting at ghost size and going down to 0. The back of the card has the identity transition, which means it just instantly will appear. So that's like no animation, right? Instant identity means that the two view modifiers are identical. So there's nothing to animate between the two of them. So it just instantly appears, it instantly disappears, the back. There's a third one, which is this rounded rectangle. Notice it doesn't have dot transition on it. The default is opacity. So that would actually fade in and out. So when this card went face up, the stroked rounded edge would fade in while the little ghost zoomed in. This transition thing is not like dot animation. Transition applies to the entire view. So if you put dot transition on a Z stack, you're talking about how the whole Z stack will fade in together, right? Or grow in together. It's not going to sprinkle them out to each thing inside. You're talking about the entire Z stack. This dot transition view modifier, like dot transition opacity or whatever, you're just specifying the transition there. The word transition can be used as a verb. People think, oh, I put dot transition, I want this view to transition. Okay, that's not what's going on here. Think of transition there as a noun. This is the transition to use when this thing appears or disappears. The way you make a transition animation happen is you take a view off the screen or you put it on screen. That's what makes it happen. Dot transition is just saying which transition to use. So think of dot transition as a noun. Again, I emphasize this because we had students in previous quarters who said, help me. I called dot transition on this thing and it never transitioned. And it was because they weren't removing it or adding it from it. So dot transition there is the transition to use. It is possible to control a transition's animation curve. You see here, I've made it so that this transition, which is an opacity fade in transition, its animation is always going to be a 20-second linear transition. That's very slow country. So you can do it. But the reason I mention it is because notice that the dot animation is not on the view, it's actually on the transition. You see? In transition opacity dot animation. I'm actually specifying for that transition, use this animation. So people get confused by that. This dot animation is part of the transition. Normally we don't do this. We allow whatever our explicit animation that's happening or even our implicit animations happen to affect it. But if you needed to override it, you can do it. That's what that is. All right, totally different thing here now, matched geometry effect. So sometimes you have a view that you want to move from one place to another place. And sometimes it's easy. It's like shuffle. When I hit shuffle and I reorder my for each, it causes the lazy B grid underneath to change the dot position view modifier on all the card views, and they move. And since dot position is a view modifier, it gets animated, its changes get animated, and woo, the cards all move around. Real easy like. But what happens if the two views are not in the same container? This won't work because you can't just change dot position. The dot position view modifier is within the container. The other view, if the place is somewhere outside the container, there's no global screen-wide dot position. It's only inside the container. To do this, you actually have to have two views, one in the one container and one in the other. And you're going to remove one at the same time that you're adding the other one to the other one. And you're going to match their geometries. That's what matched geometry effect here is. So let's talk about an example of doing this. Let's say in our memorized game, we wanted to deal the cards out. We're not going to just have them appear. We want them to deal out from a deck of cards. Well, we would have the deck maybe in the bottom corner or somewhere else. And then we would have our field of cards in our lazy B grid. They would be in different containers, clearly. I would just put match geometry effect view modifier on both of them, the one that's in the deck view and the one that's in my memorized game view. And the ID I'm going to use is going to have to be some identifier that's the same for both. Easy for our memorized game, we would just choose the cards identifier. That would clearly identify the same view on both sides. And then there's this namespace. The reason we want a namespace is we might have matched geometry effects going on between different things. Like maybe we have a deck we're dealing out of, maybe we also have a discard pile. Maybe it's a game like your set game where the cards get discarded and you want to go to a discard pile. So you might have two things going on. So you have to have this card ID be namespaced for which match geometry thing you want. So you create a namespace with an @ thing, like @ state, called @ namespace. So @ namespace var my namespace. Notice you don't have to say colon namespace. It's implicit. This thing knows that it's an @ namespace, so you don't put the colon namespace at the end. And now all you have to do is write your code so that only one of the two views is ever on screen at the same time, right? You got to match up their for eaches, the arrays that drive the for eaches, so the one's never in the other one's array. Or if you're doing if thens, you got to have an if that matches up the other one's else, so they're never on screen at the same time. And if you do that, then the view as it's disappearing will fly over to where the one that's appearing. Their geometries, their positions, and their sizes, by the way, will be matched. So even if your deck were small and your cards were big, the card would start out small on the deck, and then it would just get larger and fly over to the other one. It would match geometry. That's why it's called match geometry effect. It is possible to match the geometries of views that are both on screen. Like one's a bit of a slave to the other one, following it around or matching on top of it. There are other arguments to match geometry effect which determine which one wins when they're both on screen. I'm not really going to talk about that. I'm mostly telling you about this so you get an idea that it's out there. You will need this for your assignment 4 because you are going to be dealing the cards out and discarding with animation. So you'll absolutely need this. But you won't need, they'll never be on screen at the same time. Your cards that you deal are either in the deck or they're up showing to the user or they're in the discard pile. They're never in two of those places at once. Now, remember I said that animations only work on views that are CTA AOS. What if you want to kick off an animation as soon as you are in a CTA AOS, right? As soon as you appear in CTA AOS, you want to kick off your animation. Well, there's a really cool view modifier for doing that, which you're going to use all the time. Dot on appear. It just takes a closure, and that closure is going to be executed every time your view appears on screen. And when you appear on screen, you are by definition in a container that is already on screen. You can't come on screen otherwise. So since that's the case, you can do some animation in there. So inside your onAppear, you can do other things in your onAppear, by the way, initialize some variables, get some data ready, whatever. But you could also do inside there with animation, start some animation going, right? Change something that causes the animation. And so onAppear, and we're going to do this with, remember in the demo I showed you of Memorize, we had the score thing where you match two cards and it would say +2 and it would fly up. That's exactly what happens there. That +2 view is going to appear on screen. And as soon as it appears on screen, I'm going to start animating it to fly off using onAppear. So I told you that view modifiers and shapes are where animation happens. So how does that work? What's the engine inside of a view modifier that makes these things do what they do? Well, it's actually pretty straightforward. Essentially, as you might imagine, the animation system is going to take the animation duration and divide it up into little pieces, and it's going to ask the view modifier, okay, what do you look like here? What do you look like here? What do you look like here? All the way across. And, you know, of course, the animation system takes care of whether it's ease in, is that ease out, linear, duration. It does all that. Well, it's doing to the view modifiers, okay, what do you look like now? What do you look like now? Over and over and over. And that's it. And that's really all a view modifier has to do to work, is to listen to the animation system, draw the piece it's supposed to draw, and the animation system will take care of the rest. For example, our Cardify view modifier that flips a card over, we know that the way it flips over is bad. It doesn't look like a flip at all. It wants to do it. It's going to be piecifying the rotation of the card. All right, here's my card here actually, right? And I go from face down and it rotates like this. And then once I get on edge, then I start seeing the front and then it finishes, right? So this has got to get piecified. And that's what's going to happen for Cardify. So how does it do that? How does the animation system talk to your view modifier and tell it what piece to draw and all that? It does it through one var. This one var called animatable data is the thing that does it. Now, any view modifier or shape that wants to be animatable has to implement the animatable protocol. It only has this one var in it. The type of the var is a don't care really, but it's a care a little bit because it has to implement the protocol vector arithmetic. Vector arithmetic is exactly what it sounds like, being able to do algebra basically on whatever this thing is that you passed so that it can be sliced up into little pieces. No matter what it is, it can be sliced into little pieces. Now, most of the time, that's going to be, this animatable data is going to be a float or maybe a double, right? CG float, something like that. Maybe it's opacity or rotation. Those are going to be double precision floating point numbers. But there's a really important vector arithmetic implementer called animatable pair. And it's got two don't cares, which are themselves vector arithmetic things. Of course, you can have animatable pairs of CG floats. Now you have two CG floats that you're animating, or you could have an animatable pair of two animatable pairs of two floats. Now you have four floats that you can animate. The combination of having animatable pair and then these things that implement vector arithmetic, you can pretty much animate almost any mathematical piece of data. So how does it work that there's just this one var? Well, that var, the setting of that var is the animation system saying, draw this piece, right? So it sets that animatable data to a certain piece, and you got to draw yourself. The getting of the var is actually important too. So this is a get and set var. The getting of the var is the system getting the start point and the end point of the animation. So when we go from face down to face up, the animation system needs to know that it starts at 0 and ends at 180, right? When we go is face up 0 to 180. So it's going to ask that var before the animation starts, where am I starting? Where does your animatable data start? And then it's going to say, what's the end point? And then it's going to cut that up into little pieces, right? It can't cut it into pieces unless it knows the start and end. And it's getting that from this var. The var is important for communication both ways here. Now this var animatable data, you don't really want to be writing the code for our Cardify, and in there it's like set rotation to animatable data. You want to have a var called rotation, and you say set the rotation to rotation, right? So animatable data is often just a computed var that sets and gets some other real var. So in other words, we just use it as an alias, as a name, just so we can communicate with the animation system. You'll see that when we do our Cardify, the var we're going to animate is rotation, but we still have to make it come in and out of animatable data, so we'll have a computed set get var for animatable data that sets and gets the rotation. So that's it. That's all there is pretty much to animation. Of course, I'm really just showing the highlights of animation. All of these things have an enormous amount of depth to them, which you'll learn over time. But let's go through the demos today and on Wednesday. You'll see all this stuff happening. It's going to make a lot more sense when you see it in code, as with most things. All right, I told you that the first thing we were going to do when we got in the demo is get rid of that implicit animation. That's this right here. This is what's causing shuffle to cause this animation to happen here. If I take it out, then shuffle becomes instant, just instantly. It's not moving them around. Remember, I also said, I'm going to put it back here, I told you that when I click shuffle, whatever happens in here happens instantly, and it's just taking time to show it to me. You can kind of see that when I click shuffle really fast. You see, it doesn't quite, the cards don't get to their new position before I start shuffling them again, so they just start heading to the next new position. That's because I'm instantly changing the order of that, and it's instantly changing in my code, and the animation system is just trying to catch up as it desperately tries to do that. But we would never do shuffling like that, because shuffling is response to user intent, right? To view model intent. So we would actually do it right below it here. We would say with animation, shuffle the cards, please, which also reads better from code-wise, because that's really what we want. Please, with animation, shuffle. And now, if we go back here, got a couple cards and shuffle, it's back to fully shuffling every time I click shuffle, because that's an intent by the user, and I'm animating that intent. But something has definitely changed, because watch this. Clicking a card, instant. When we had the implicit animation up there, when I clicked on a card, it faded in and faded out because that implicit animation was applying to any change to the cards, not just shuffling, but anything. Whereas here, we've made it specific. This animation is specific to that. And we can, of course, control the kind of animation we want here. So we know that ease in out is the default animation. That's what we've seen so far. We could also control the duration by making it be an ease in, ease out with 2. So watch this. And this, by the way, is a great way to debug your animation. I'm going to say this right off the bat. When you're doing your assignment 4, set your animations to take a long time, and then you'll really see what's happening. Is it really fading in? What's actually happening there? And we could use other curves. Maybe we can tell the difference here. Ease in, ease out looks like that versus linear. We'll see this later. It'll make even more sense, but see, it's kind of same speed all the way through the curve. How about that funky spring thing I told you about? We'll use an interactive spring. We'll do a response time about 1 and damping fraction maybe 0.5. And here we go. See how it has a soft landing there? And we can control the damping to make it more springy or less springy or whatever. That's how we control the animation that's going on here. But most of the time, we don't want any kind of funky animation. We actually want the default animation because we want users to have the same experience they're having in all the other apps. If we're using an animation curve, we want to have a pretty good reason. Now, when I hit shuffle, what's actually happening? Well, what's happening in there is I'm rearranging the order of the cards. That's causing the lazy V grid to reposition all of the views inside of it because the for each has changed its order. Just using the position view modifier. All that's really being animated when I click here is the arguments to the position view modifier inside the implementation of lazy V grid, which we can't see, but still all view modifiers that change are being affected here because we're explicitly animating everything that changes with that user intent. Let's go back down here to our choose a card and give it animation too. With animation, choose the card. Now when we have this and we tap, see, we're getting the fade in effect. We'll see it a little better if we ease in out duration 2 down here. See it's fading in, fading out. Interestingly, shuffle is still fast. Shuffle doesn't take 2 seconds because its explicit animation doesn't have ease in, ease out duration 2. All right, let's take this back off and just use the default animation there. Let's talk about when we would use implicit animation. We took that implicit animation off of there, and I told you we would never do it that way. Well, when would we use implicit animation? Well, how about if we make it so that if we get a match like this little ghost guy does a somersault, acceleration somersault. Let's see if we can get him to do that. So where does that happen? Well, it's in our card view over right here. This is the ghost, right? The text that's inside of our card view. I want that text, that ghost, to do a flip when the things are matched. Real easy to do. You can do a flip with a rotation effect you saw on the slides there. It just takes an angle, let me say degrees, and we'll have, if the card is matched, we'll do 360 degrees, otherwise 0. So that's a rotation effect. And if I go over here and match, whoop, he did it. See how it's so fast you can barely see him there. And maybe that's a little too fast. It's so fast that I don't really get to celebrate my victory very long there. So I want to affect the animation. So this is where I would do an implicit animation here. Maybe an ease in out. Maybe I want the duration to be maybe 2 seconds is too much celebration, but we'll see. And I'm only going to do this when the card is matched. There's no reason to apply this animation any other time. No other change should cause this animation. Let's see what happens here. There he is, and And now you can really see the ease in, ease out, right? Let's also go and make this so we have fewer cards. So the cards are bigger. See the ease in, ease out happen, where he starts and then he speeds up and he slows down. What if I wanted him to keep spinning? Okay, he did a nice flip, but what if we just wanted to spin forever? Well, we can go in here and say repeat forever. That's what that looks like. Well, it is repeating forever. That's good. And you can really see the ease it is out now because he slows down every time he turns around. But what I really wanted was for him to keep going round and round. I didn't really want to go back and forth and repeat by backing the animation up and then making it go forward. No problem. Inside repeat forever, we can say auto reverses. False. Don't auto reverse, please. Yeah, it goes around and round. Again, his ease in, ease out is causing him to stop each time. Let's get rid of that. Make this be a linear animation. And that's a little slow. Like maybe something like 1 second to do one full turn. That's pretty good. So here's where you might use an implicit animation. You want this to happen no matter what's happening. For example, shuffle keeps doing it. Why would it stop? My match is still showing. I should still be celebrating it. It's completely independent of any other with animation or anything else going on. And it overrides it too. When I did the with animation, it didn't use my shuffle duration or something like that. It used this duration and this linear curve and all that stuff. It's overriding what the explicit one is doing. And another thing we would do here, which is kind of interesting, see this little animation right here? This is kind of an animation I might want to use other places, spin animation. I'm going to take this off here. I would really like to be able to just say spin duration 1, for example. So how could I say that? Well, extensions. So here's a good example of when we can use an extension. So I'm going to extend animation, and I'm going to add a little static function called spin, and it's going to take a duration, a time interval, and it's going to return an animation. And I'm just going to return that linear thing that I had up there. So now I made a new kind of animation, animation.spin. It compiles, no problem. Works fine. Now, let's talk about the real animation problem we have here, though, which is this animation. Card is face up. We want it to turn face down. Let's take a close look at what we have right now with that, which is, in fact, I'm going to go in fewer cards, make this really large. So we have total just fade right now, right? It fades in, fades out, fades in, all right, see that? Fades out. That's clearly not what we want. We want it to rotate in kind of a 3D manner, not rotate like this. Rotate, in fact, we want it to rotate like this. Well, there's something that actually does that. Here I'm in my Cardify. Obviously, this flipping of the card is a Cardify thing. Does nothing to do with a memorized game. It's flipping card. You can flip anything on here. So let's go add on our Z stack in Cardify. I'm in Cardify right here in our Z stack. Dot rotation 3D effect. So it wants an angle as well. This is degrees, and if I'm face up, then let's say 0. And if I'm face down, 180 degrees. I want to rotate from face up 180 degrees. Everyone agree this is 180 degrees? And the axis is interesting. These 3 numbers, X, Y, and Z, specify where you are. So this is obviously Y, this is X, and Z is out towards you. And you can have this thing rotate on any of those axes. If we had it rotating around X, it would flip this way. We're going to have it obviously go from Y, so it flips like a card does, like we're flipping a card over. And we can specify those here. So it would be 0, 1, 0, 0 in the X direction, 0 in the Z direction, just 1 in the Y direction. That's all it takes. Look at this. Whoop. Nice. And it's a little hard to see. It's going so quickly, we can't see what's going on. So let's go back up here to our choose explicit animation and make it so that it takes maybe 3 seconds. Seems good. Here we go. Ready? Now that's not quite right. It's so close. Not quite right. For example, notice that when my card starts from face down and it starts going, you start to be able to see the front. Can you guys see the front? No, there's no front. But on here, it's starting to fade in. This front, you can see the front. What? You shouldn't see the front until you get here, right? Once you get to straight up down, now you should see the front, and you shouldn't see the back. So somehow we can make it so that it switches over without this fading. Essentially, we don't want this opacity right here to be animated. We want it to happen instantly as soon as we get to 90 degrees. Well, there's no way to do that other than to have the view modifier itself control the animation. It has to be involved at every piecewise turn of that rotation so that it can make the opacity be right when it switches over from being on edge here. How do we do that? Like I talked about in the slides, we're going to make our view modifier be animatable, which means we need this var animatable data. And it starts out with empty animatable data right there. And what is our animatable data? Again, it's that rotation. I don't want to call rotation animatable data everywhere in here. I'm going to have a var called rotation. It's just a double number of degrees. So I have this animatable data here, be that double, but it's going to have a get, which returns my rotation, and it's going to have a set, which sets my rotation to the new value. So this is computed property, right? Remember from index of one and only face-up cards, we're doing the same thing here. We're just getting and setting the rotation directly. Every single time the animation system talks to us about a slice, we're talking about the rotation. And the reason we do this is so that we can use rotation down here in our implementation, not animatable data, which is just a bad variable name. So where do we need a rotation? Well, clearly, our rotation 3D effect wants the rotation. We want to pick a 3D effect, which is that rotation. Now, we have to say this is the rotation because as soon as we start providing this animatable data, these animations stop working. These animations don't work anymore because we put that and we told the animation system we're doing the animation. So stop automatically animating our stuff in here. Let us do it. So I need to piecewise rotate my card. As the animation says, oh, you're at 1 degree, 2 degree, 10 degrees. I need to be this many degrees rotate 3D effect. What about my opacity? If I redefine is face up to be 90 degrees or less, then this will still be right. So let's do that. Let's go up here to is face up and just have it be a computed var whose value is rotation less than 90. Now is face up is computed to be the right thing. As long as rotation is less than 90 degrees, face up is showing. As soon as it's not 90 or more, now we see the back of the card. The problem is down here. Look at this error. Cardify is face up, face up. Well, oh yeah, okay, I've changed its rotation, but I don't want someone who's calling Cardify to have to say, Cardify rotation equals 0, okay, or rotation 180 if it's up. I still want them to say, Cardify is face up. How would I do that? Well, how about an initializer? Init is face up. It's a bool. And if is face up, then our rotation is 0. Otherwise, it's 180. I'm using my initializer there. It still says is face up, and it's just setting the rotation to either 0, this, or 180, this. This protocol, I'm going to click on it so you have an idea of what this looks like in the documentation. You can see that this protocol only has the one var in here, animatable data. And notice this has associated type animatable data. Remember the slides from protocol? I told you that don't cares for protocols, this is a protocol, they have this associated type thing. So that's what you're seeing here. That's why I showed you that slide, so that when you see things like animatable data, you realize, oh, this thing has a don't care. That don't care is the return value of that var, see? And it has to care a little bit, implement vector arithmetic. And then from here, you could say, okay, well, vector arithmetic, what is that? Click on vector arithmetic. Here it is. It inherits from additive arithmetic. And in fact, it's able to calculate default implementations of vector arithmetic from additive arithmetic. If you go there, you can look and see, well, what implements this additive arithmetic? Here they are. All right, now let's see if it works. Ready? We got this. Here's our is face up, rotation. Put this code all on here. Ready? Whoop, worked, right? No more opacity. There's no opacity involved here because once we took over by implementing animatable data, these things stopped being automatically done, and now they're being done by us. Now, I'm not going to ask you to do your own animated view modifier in assignment 4. I'm really showing you this more so that you understand what's going on inside of all those view modifiers. Now I want to start doing some of the animations like the flying number and things like that. So let's go back to our model and implement scoring. Now you all did this. Was it assignment 1 you did scoring? Assignment 2. So I'm going to go back to my model here and I'm going to add scoring, which of course is just private set var score, which I'll have start out as 0. And then down here in our choose, when we have a match, right, these two things are matched, we're going to say score plus equals 2. I think we got 2 points for a match, right? And then we had -1 when we had a mismatch that we'd already seen the card. So let's put that in there. If we don't have a match here, then we're going to say if the card at the chosen index has been seen or something like that, then score minus equals 1, and the exact same thing for the potential match. So what about this has been seen? Where do we set that? Well, that's just something on our card down here. Cards can be face up, they can be matched, and they can has been seen equals false. I assume you guys had something like this. Somehow you had to keep track of whether a card's been seen. How did you set this? Well, I'm guessing you set it up here in index of the one and only face up card, or maybe you set it, I don't know if any of you left the card flipping down in here somewhere, but wherever you flip the cards back face down, you probably set has been seen, which is great. But there's another way to do it now, you know, which is the property observers that I showed you earlier. So here I'm going to say in is face up, whenever you set it, if the old value was true, so it was face up, and it's now not face up, so you change it from was face up to not, then has been seen equals true. Voila, property observer, really easy to set this. And we're going to use this property observer, obviously, for the pi thing. I was to stop and start using bonus time as well. Now we just need to put the score in our UI. So we're going to bounce back here to our view model, expose this from our model to our view. Score is an int. We're going to return our model's score. And of course, it should do that. By the way, I have to say, having seen some of your assignments, please, I've said this many times, don't call your model var model, and don't call your view model view model. I'm calling it that so you learn it. You want to call it something meaningful like game or something like that, something what it is, the var what it is. So we had our score in the view model, pop back over here. Let's put the score along the bottom next to the shuffle right there. I'll make a little H stack. The text says score. Put the view model, that score in there. Maybe put a spacer in between. The button inside the H stack. I don't tend to tell you about command keys and stuff like that, but this one's really valuable. If you select the curly brace thing here and do Control I, it will move all the spacing. So I for indent, so it's like the automatic indenter. I mean, it mostly tries to indent as you type, so you don't need it much, but if it didn't do it, like it didn't do it there. And since this is a demo, I'm going to make these large fonts. This is another thing like calling the thing model that you wouldn't do in real life. But I just, on the screen here, I want you to be able to see these things large, but you wouldn't make your buttons large title. That just wouldn't make sense. I'm going to take the time to do this right. I don't like this body. It's too many lines of code, too hard to see exactly what's going on, too many curly braces and all that stuff. So I would actually take the time in real life to say, I'm going to make a private var called score, which is some view. I'll put this text in here. Even though it's only one line, it's still naming it. And then same thing here for shuffle. Some view and put this in here. And then that lets me go back up here and say score, spacer, shuffle. And this just makes this more understandable. It's easier to read what's going on. It's not about the fact that, and I actually added a line of code here. I have 2 lines of code where I only had 1 up there. But this line of code is a naming line of code, and naming, computer science is all about naming. Arguments have been made that that's all it is one gigantic naming exercise. But you can see how it makes my code look a lot better, the code that's selected there. And I really want you to do that. Not to mention the benefit of it's a lot easier to debug your view builders when you have small little view builders. Because when they have an error in there, sometimes they give you an unfathomable warning. What is that? But if you break it down into small pieces, then you'll see at least where the warning is coming from. Now, let's take a look and see how things are going here. We got this. Got a real slow turn. Let's see if our scoring is working. It is working. See that too? Although, one thing I don't like about it, watch this. Let's make that match again. First of all, let's speed ourselves back up. Let's get choose. We'll go back to normal speed here. All right, so I'm going to pick this, flips over. Now watch my score down here. You see that it faded in? The 2 faded in. Nah, I don't like that. I don't want to fade there. I just want to appear. So how do I stop it? Because the reason that's happening is my explicit animation is saying, hey, animate everything that happens when I click a card. Well, that happens when I click a card, so it's animating that. How do I stop it? Well, implicit animation, dot animation nil. So it turns out that animation that the thing takes is an optional, and you can specify nil. And that means do not animate changes to this view. Now watch our score down here. Click, ready, bloop, instant 2. So dot animation nil, nice little thing to have when you want to turn off animation. Flying number. We're not going to get all the way through flying number, but let's get as far as we can get here. How am I going to do my flying number? It's actually going to be quite easy. I'm just going to put a number, which is whatever the score changed, and then when it appears, I'm going to animate it flying off and opacity going to 0. So the animation is actually quite easy. You already know how to make the opacity go to 0, and the moving it also turns out to be just one view modifier. But I got to get this number on here somehow when the score changes. Oh, let's talk about where I'm going to put that. I'm going to put that on my card view, right? When I click on a card, if I got 2 points, like +2 is going to appear right here. If I click here and I had a mismatch, -1 might appear here, and that's going to move over. It's going to appear on my card view. Let's say dot overlay, because it's going to overlay on top of it. I'm going to create some view called flying number, and the flying number needs the number to put on it, like number. And I'm going to create a function for this, score change caused by this card. That's what I want to put on when I click on a card, right? I want the score changed that this card caused, +2, -1, whatever. I'm going to write that function. Well, let's go down here and say private func score change caused by card. And it's going to be some int because of my scoring is integers right there. Now, I can't say card here because this is what? What's that type? memory game of string.card. I am going to immediately go up here and save myself some typing by putting a type alias in there. Card equals memory game of string.card. Now let's go down here and I can have this just be card. Now let's return 0 for now, I guess, but we're somehow going to have to calculate what the score change is that went to that card. Before we do that, let's go stub out or start to implement that flying number, and that's where we'll end today. And then when we come in on Wednesday, we'll get it animating and figure out how to get that score change going. So flying number, I'm going to go here, File, New, File. This is a Swift UI view, so lower left corner. It's called flying number. Make sure it's in the right place here. It is. Create. Here's our flying number. Created its own file for it. That's great. We know that our flying number needs a number, so we'll say let number be an int. And inside its body, it basically just text. It's like the text of a number, which you'd like to just say that, text number. Wouldn't that be cool? But we know that the argument to text is what? A string. So we could do this, quote, backslash, number, right? Could do that. I'm going to show you another cool thing about text. It knows how to take other data types like number and format them. So it has a format argument, and one of the formats it has is a number formatter. And we're going to see that we're going to put other arguments on this number formatter, but that's a nice feature of it too there. And let's go down here to this and say, number 5 is going to be our preview number. And what else do we want to do here? One thing about my flying number, I never want 0 to appear and fly. Do we all agree with that? Which only score changes where it's like +2 or -1 or something that changes. So I'm going to put an if number does not equal 0, then I will do this. That's going to keep zeros from popping on my thing all the time. That is as far as I'm going to go. We're out of time. And just a little preview of what we're going to do next. We're going to implement this score change. And the fundamental technology I'm going to use for this is something called a tuple. And hopefully you all know what a tuple is because you did your reading assignment, I hope, and you paid attention. But a tuple is a really nice little data structure that you can use for exactly cases like this, where you need to kind of keep track of a couple of things together. In our case, we need to keep track of which was the last card that was chosen and what was the score change. That's a couple pieces of data that need to be stuck together all the time. And yeah, I can make a struct for it and all that, but it's just nicer to use a little tuple. So we'll do that to start on Wednesday.